Good afternoon, everyone. My name is Felipe Ruiz, and today we will present for you about our article titled Construction Materials Flow Investigation, Delay Evaluation in a Sand Supply Chain with Simulation. The increasing competition in today's market and decreasing profit margins create the need for more significant investment in planning and control, leading to studies to find solutions that reduce waste and losses in the sector. The principles of lean thinking meet the demands of current context and have as their starting point the elimination of waste. Lean supply systems require integration into the production process, which means minimizing waste. Integration allows better synchronization between supply and demand, bringing material to the workplace. The purpose of this study is to evaluate the effects of using a delay generation system on the construction order time and delivery interval in a sand supply chain, measuring the impacts from supply chain model simulations. In the model presented in this article, the sand flow was evaluated in a case study of a 300 meters square single-family residential building construction. The development of the simulation model of this study was based on the works of Ruiz, Fontanini and Correia, 2019, and Ruiz and Fontanini, 2014. The period between the first and last request for sand delivery was 300 days. Shipments were weekly, made in a 6 cubic meters truck. The ordering interval for sand work was, on average, 2 days, and the delivery time was 3 days. With this information, a computational model was elaborated in the Stella software, simulating the work scenario. Within the model was inserted a delay system that influenced the order and delivery intervals and an accountant. The collected data allowed the visualization of the impact for the construction. The delays during the simulation varied handily. As for the delay in the work order interval, a maximum tolerance of 1.5 days in a month was considered. Therefore, with the delay system ranging from 0 to 5% in the observed delivery times. Regarding the delay in the restoration interval, the tolerance was 2 days late in a month, which resulted in a 0 to 6.66% variation in its delay generation system. These grace periods were considered based on observations of the actual case study arrears. A total of 100 simulations were performed on the model. The generated data were evaluated for the mean, median, standard deviation, coefficient of variation, amplitude, maximum, and minimum values. Based on this assessment, the impact of delays was measured on both the expected total lead time and the costs relative to the waiting times. This research used the Stella software version 9.1.2 for the simulations and Microsoft Office Excel 2016 for the statistical analysis. After completing the supply chain modeling, it was verified as to its functioning, comparing the results generated with the data of the case study. With the model developed, shown in Figure 1, 100 simulations were performed, and their data related to the losses caused transferred to the Microsoft Office Excel software. The structuring of the production flow started by collecting the ordering and delivery intervals for the sand. The sand supply chain data from construction were analyzed from the execution of the foundations to the finishing. This supply chain has been digitally recreated using programmable inventory and flows functions. After overrun the model 100 times, the results analyzed present an average loss of $1,993 with a standard deviation of $51.08. Figure 2 shows the relationship between losses and the frequency of occurrence within the model. Through the visual analysis, it was possible to verify that even with the simulation using a system of variation of random delays, at the end of the analysis, a behavior was perceived in the obtained data. An equation was developed that allows a quick assessment as to the frequency of occurrence of the simulated data when launching the interested value of loss. Through the analysis of the data, a relationship of coverage of the results with loss was obtained, present at Figure 3. Using this graphical analysis was to elaborate a correlated equation for the data coverage and loss. Using a desired scope, it was possible to calculate the possible loss. This equation freed up more help for making difficult decisions, quickly evaluating or impairing average performance during the execution of a limited percentage. Through the statistical analysis carried out in this study, it was possible to evaluate the effectiveness and precision of the model elaborated with a close approximation to reality. This study allowed the visualization of the impact of the delays with a greater clarity and a better understanding of their behavior. It was possible to verify the significant influence that the delays cause on a residential construction flow and the harmful effects of the absence of a stock and supply system control. In the case study, the average loss generated by delays within the sand supply chain for the single-family residential project was of $6,251 or $1,742. The model considered only the costs related to labor. The impact of materials delays was not assessed in this study. Due to the absence of a control system over orders and delays, it would be necessary to consider an additional cost in the work of approximately $6,543 or $1,823, in addition to the price initially foreseen, to cover 95% of possible losses. Through the analysis performed, it was observed that the range of results regarding the loss at the end of the simulations was approximately $840 or $234, almost equivalent to hiring another mason's assistant. Such findings demonstrate the importance of having an inventory control system, which would allow for the ordering of materials in advance, before they are finished, and of having a control and evaluation system for their suppliers, which would guarantee on-time deliveries, thus minimizing impacts and losses on the supply chain, increasing the efficiency of the system. Apply such controls, it will be possible to stay within the costs initially provided for in the project. In addition to the direct impacts caused by the delays, the other financial consequences resulting from the situation must be taken into account. Since, with these days, there will be a consequent decrease in the profit margins previously stipulated, and the amount of the loss could be used for purchase. The model structure used in this study has potential for implementation in other construction supply chains. A proposal for future studies would be to implement this model in order flows, assessing the impacts of delays in the monetary sphere. With this information, it is possible to better assess the risks and aid decision-making, allowing for better based planning. We would like to thank the State University of Campinas for the support and provision of the necessary infrastructure to conduct this research. Thank you very much for your attention.